Good afternoon. Just a few minutes, and then we will start our lecture today. Okay. Okay. I will turn on the recording on the lecture and next share my desktop. Okay. Oh, well, we focus our stability analysis on determining this is the reference equation of our stability analysis. This is the question here, and we presented this problem as a generalized eigenproblem. And the scope of this problem is to determine in such a numerical way the S value such that the determinant of this equation bracket be 0. Okay, so we dedicated past time on the procedure, uh, different procedure for determining this generalized eigenvalues as or poles of our aeroelastic transfer function matrix. And we discussed the fact that we have a couple of possibility, an iterative possibility and a standard possibility based on the use of finite state representation for the aerodynamic and so and so. But we never focus our attention on the eigenvector W. What this complex eigenvector are representing for our analysis. So I would like to spend some time on this element of our stability analysis, the eigenvector W. Okay. So some comment about the complex eigenvector W and corresponding to the eigenvalues Sn in our problem, in our generalized eigenvalues problem or Frater problem in elasticity, which consists of solving this system, as you know. Okay, and we have n eigenvector and eigenvalues for n equal to 1, 2, and this is an interesting point, not capital N, if these metrics are n by n. In a standard way, we should have n equal to maximum to n, but this is not the case because we have a transcendental dependency here, and therefore we should have something more here. Okay. However, we discussed the methodology for evaluating. First step is the evaluation of Sn by taking the determinant of such a quantity in bracket and imposing this quantity to be 0. And then we have a second step. We want to focus on this second step, the determination of Wn such that this is verified for all n. And here you have to put inside the found values for Sn. Okay, so at the end of this generalized, this is a generalized problem, generalized eigen problem, we have these two quantity W and Sn, and we can build our free time response of our system to initial condition. And we have Q, function of time, is equal to combination of constant multiplied by the found eigenvector by e to the power SNT, and we have to sum all this contribution. We have a couple of eigenvalues, complex conjugated, so you have to sum all the complex contribution, including the complex conjugated, in order to have a real response like that. So we have to sum all this elementary solution, and this constant, as you know, as you remember by the number 1 exercise with panel flutter, this constant are given by the initial condition. Okay, so the free time response for our aircraft is finally evaluated, do not forget, by building your displacement as the combination on the all the Q quantity. So these are the structural mode. So use another index like M from 1 to number of mode. And you have to sum the structural mode, which are your shape function, shape of structural mode, by this time quantity obtained by the free response like Q and function of T. Okay, so this is our free response, and I would like to comment with you this free response, this free time response, by involving and by considering the role of our complex eigenvector W. The complex eigenvector W are the actors, the main actors in this response, because we have to consider this this contribution. Is it okay? This contribution in the evaluation and building of the free response Qt. This free response is represented by the variable Q, which are currently the modal coordinate. Okay, so the story is we have introduced modal coordinate structure in structural dynamic, but in that motion representation by the modal coordinate, we have considered also the contribution of the coupling with the aerodynamic by solving our critical equation here. Okay, and this is a preliminary point for better understanding the how can I build the free response. Now, when we perform a flutter analysis, the scenario of the stability is given by a root locus. For example, we could fix the density, and we could variate U in a root locus like this, and like this, and like this. So we had originally 3 mode of vibration, and here we have a symmetry of the root locus, and increasing the velocity from 0 up to a value, for example, 300 meters per second, we have this root locus scenarios, and therefore for this critical value of velocity we have a flutter. Okay, so when we have u equal to u flutter, we have a critical pole S equal to j omega flutter, and this is our critical pole. In this critical pole, the other poles are typically stable like this. So with this black bullet, we have the pole, red ball, excuse me. We have poles corresponding to the flutter velocity. So in flutter condition, we have a marginal unstable pole like this, equal to, and all the other are stable. The other poles are stable. Okay, so what about the motion? The free response in flutter condition. The free response to flutter condition is typically given, is indicated like here we have a motion in critical condition is equal to x time, and we have again a combination of the m mold shape of vibration, structural mold shape, and in critical situation like this, we have here q model coordinate critical. And what I mean for q critical functional time, and with an index m. Q critical is exactly this q here when you are in margin condition, where you have all post stable but one is marginally stable. So Q critical can be defined as the following. We have that Q critical is equal to Q critical vector in the sense that here we have an index. So here we are indicating the array Q critical, which is equal to the summation of Cn, as we told before, Sn T W n. But since we are in this critical condition, we have something like almost equal to the margin pole, which is e to the power j omega flutter t, which is this here, j omega flutter. So we have j omega flutter by t in time, and here we have the famous critical, the famous critical eigenvector like W critical. And this elementary solution is the critical solution, the marginal solution. And we have to sum this solution multiplied by a constant C. Here we have E, the Euler number, and we have to include in this summation the complex conjugate of this plus stable poles contribution like this, like this, stable contribution. So this part of the time response is decaying, and if we do not consider this, we have this approximation. So in steady state, in an oscillatory steady state, we have an oscillatory solution given by the only contribution of the flutter mode. Okay, so now we want to express more explicitly this kind of solution, and so we want to develop this Q critical contribution as equal to our, again, I want to reply again, this contribution J omega critical T W vector, the critical vector, and plus complex conjugated. And what happens when you sum to a quantity a complex conjugated quantity? We have 2 times the real part, 2 times we have this C can be taken as real without not loss of generality, because we are talking about the solution avoiding any contribution of the initial condition. So 2C, and here we have to write the real part of exponential is a cosine omega critical T plus J sine omega critical T. This is the exponential. And then we have our famous complex eigenvector. This eigenvector has a real part, is a critical eigenvector, plus an imaginary part, J E critical. And we have to close this, we have to take this real part. So in order to have only the real part, the real part contribution is given by the cosine multiplied the real part of the eigenvector, and minus the sine multiplied the imaginary part of the critical eigenvector. And therefore we have the following for our Q critical in time. We have quite a real function, not complex, of course, because our system is a physical system, and we have only real quantity marching in time. And so 2C, and we have the real part of the eigenvector. Let me write better. We have the real part of the critical eigenvector multiply the cosine of omega critical T, minus we have the imaginary part of the critical eigenvector multiply the sine omega critical T. And this is the time history of our system in critical condition, avoiding the contribution of the stable part. And now let me rebuild our U quantity. This displacement vector, excuse me, let me have another whiteboard. Excuse me. Okay, so we have as U critical vector in for any material point in any time. This flutter vibration is then represented by a Q1, which is 2C, and we have W R critical eigenvector cosine of omega critical T minus W critical imaginary part sine omega critical T. and this is multiplied by psi 1. Look, first structural mode, first component of the critical eigenvector, first component of the critical eigenvector. And this is the first component of the critical eigenvector. Function of time is exactly the first time function of this vector. In order to have the first time function of this vector, you have to take the first component of WR and WI. Okay, so we are actually rebuilding our final solution, and so we are considering the first mode of vibration as a function of x, and we have associated to this first mode, we associated the first modal component of the eigenvector. Next, we have the second mode contribution, so we have 2c, and here we have W, critical, real part, cosine, omega RT, minus W, critical, I, sine, omega critical T, multiplied by psi, and here we have in red the contribution of the second component of the critical modal coordinate, 2, function of time, and here we have the second component of the eigenvector, the second component of the complex eigenvector referred to the second mode of vibration. Okay, and we can include plus the contribution number 3, number 4, and so on. And let me focus the attention on this. Look, if you divide this quantity by, where is it? Okay, if you divide this quantity by the magnitude of this complex number, W1 complex, the first component of the critical eigenvector, if you divide it by the first component of the critical eigenvector and you multiply by the same quantity, which is the amplitude of the first component of the critical eigenvector, and you do the same in the other quantity, you have that this here is the ratio between the real part and the magnitude of the complex number. So you have a complex number, you have the real part of a complex number zeta and the imaginary part of a complex number zeta, and you are taking the ratio between the real part and the magnitude, and so you have the cosine of the phase of the complex number, and here you have the cosine, the sine of the phase of your complex number, here dividing the imaginary part with respect to the magnitude. Excuse me. So we have this quantity this quantity and this quantity are representing here the cosine of the phase of the complex number W1 critical, and this is the sine of the phase angle of the complex number of the complex number W1 critical. And I can do the same here. And so at the end of my story, I have the following. I have that the time history of my body in flutter condition, in critical condition, is equal, apart an arbitrary constant, is equal to C, which is a constant. And here I have the cosine of, excuse me, first of all, I have this amplitude to be considered. I have the magnitude of the complex number W critical first component. I will write this first in red later. I have this quantity multiplied by the cosine of the phase angle of W critical first component by the cosine of omega critical T, and here I have minus the sign of the same complex number is W critical by the sine of omega critical by T. And this quantity are referred to the first component of the critical eigenvector. First component, and multiplied by, and this is an algebraic first component, but it's referred to the first mode shape of vibration used in the analysis, indicated by psi1 again. And we have similar quantity referred to the second, the third, the fourth mode of vibration, second, the third, and so on, plus the other. So if you better simplify this quantity, you have this formula is we have already found this. This is the formula of prostopheresis. So you have a cosine of an angle, you have the cosine of another angle minus sine of this angle and the sine of this angle, and therefore we have the cosine of the sum of this angle. And so at the end we have that the vibration in critical condition is at the end the combination of the time function. This time function is the following, is given by taking the first contribution is related to the first component of our complex critical eigenvector as this by cosine of omega critical T plus a phase angle, which is the phase of the complex number W critical, first component multiplied by psi x, the first, plus similar contribution for the other mode. So we have here, for example, 2c W critical second component by the cosine of omega critical T plus this omega critical phase multiplied by psi x second angle plus all the other. So we have 2 and 2 plus 3, 4, all the other contribution. And what is the end of this story? The end of the story give us the capability to quantitatively define how the single structural mode are able to contribute in the flutter oscillation. Uh, I want to imagine to have an aircraft. You have an aircraft and you perform the flutter analysis in an aircraft. And before to do the flutter analysis, you could perform the model analysis. If you have a model analysis, you may have, remember this, you may have oscillation like this. Remember this movie? Remember this? You may have, in other words, you may have in the hangar at the ground, you may have a mode of vibration for your aircraft or for your elastic or flexible wing. You may have a first mode of vibration, a second, which is, for example, pure bending, mainly pure bending. A second mode of vibration should be almost a torsion. But in critical condition, you will have something like this. And what is this? Is bending? Is it torsion? How this vibration is related to the original structural mode of vibration, which is the relationship between this couplet vibration, fluid structure interaction vibration, with respect to the pure structure vibration. And the response to this question is just written here. It's just written here in what I present to you. We have in this formula we have the answer to our question. This U critical is what you see during the flight in critical condition. Is exactly what you see before. You saw before looking to the movie involving the B-52 aircraft. You see this kind of mode, this kind of motion. And this motion is a combination of this time function, which is the Q critical 1 function of time, and this is the Q critical 2 function of time, multiply the mode shape, structural mode shape. So is your flutter oscillation mainly dominated by the first mode shape? The answer is it depends on Q1 critical, and Q1 critical is dominated by the first component of your critical eigenvector in amplitude, in magnitude, and in phase as a complex number. How the second structural mode is relevant in your flutter vibration? You have to consider this Q2 critical time function, and this Q2 critical time function is composed by an amplitude given by the amplitude of your complex eigenvector and a phase shift with respect to all the others time contribution, and this time shift is given by the phase of the complex number W2 critical, and so on for the other. So at the end of the story, the magnitude and phase, and the magnitudes and phases of W critical component regulate the contribution of structural mode of vibration on the final aeroelastic mode. And this final elastic mode is a mode in critical condition vibrating with a unique frequency, vibrating with a unique frequency, omega critical. Everything is vibrating with in time with omega critical. And this is what you can see here. Everything is vibrating with a unique frequency, omega critical. You can see a frequency, ho, 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 unique frequency. Everything is vibrating with a unique frequency. But all the point of the aircraft are not reaching the maximum or the zero value or the minimum value of the vibration in the same time. You can see clearly a phase shift between one point with respect to another point, and this is the role of the fact that the eigenvector is a complex eigenvector with a phase for each component. Okay, look here. This is just like a dance of a dancer here, because you see that in this vibration, look, you can't see the maximum and the minimum of the vibration in the same time, but you have something of shift. This concept is essential to understand what is a vibration given by a complex eigenvector, which means include, please, a shift between an oscillator and another oscillator. You have oscillator with the same frequency, but each oscillator is vibrating with a different time shift. Let me do an example, a clear example to all of you. Can you see everybody, my face and my right hand like this? If you consider this motion, which could be a bending, and this motion could be a torsion for the aircraft. Okay, if you consider a pure bending mode of vibration, if you impose this as initial condition and release, you have this bending motion. In the structural bending motion as mode of vibration, you see that all the points on my pen are reaching the maximum and the minimum of the oscillation at the same time. So you have something like this. And this is a mode of vibration. You put an initial condition, you release, you have this. All the points reach zero, maximum, minimum in the same time. This is a mode of vibration, and this mode is also known as real not complex, real mode. The same with the torsion. If you have a torsional mode, you have this torsion release, you have this. You may have coupling between bending and torsion, but the concept is the same. If you have a coupled structural mode between bending and torsion, you put this as initial condition, release, and you have this. This is a real mode or structural mode, which is, in this case, there is a bit coupling between bending and torsion, but you have a real mode. What about the difference with the complex mode? If you have a complex mode, you, as before, as I showed to you, you may have this motion with a frequency, okay? You may have this motion with the same frequency, but you have to combine these two motions in order to have a time shift between the two oscillations with the same frequency. How can we do this? In the sense that the maximum of vertical translation is reached in a time which is a different time when you reach a maximum of the torsion. And what is the result of this combination? The result of this combination is the following. I can do this just using my finger in order to regulate the reaching of this maximum, and I may have this effect here in this way. Can you see? Can you see the dance, just like the aircraft? This is a complex mode oscillation. This is a real mode oscillation. And this is the difference between a flutter mode and a structural mode. Okay? Is this clear now? Now this concept is clear physically and mathematically. Just observing this relationship. Okay? And this is the concept of, and this is the role of the eigenvector in your flutter analysis. After evaluating your pole, if you evaluate the critical eigenvector corresponding to the critical eigenvalues, the role of the critical eigenvector is a complex vector such that if you have a critical eigenvector, I want to write this critical eigenvector here. If you have a critical eigenvector, you have a vector of a complex number. The first one, the critical 2, the critical 3, and all the other. If 1, 2, 3, and so on were the index associated to the first mode of vibration, the second structural mode of vibration, and the other, the final flutter combination is a combination of this 1, 2, 3 complex number which are able to modulate and shift this elementary vibration by using this formula. And the character able to do this shift and this modulation are the component of the complex eigenvector. Okay? Okay. I want to stop here for a pause, and let's take together a pause of 15 minutes. Thank you.
Professore,
Mhm.
potrebbe riprendere quest'ultimo concetto? Cioè, nel senso, il fatto che ci sia questo sfasamento nasce dalla presenza di un vettore
Complesso?
complesso?
Certo.
Quindi, cioè,
Scusi,
perché...
quando
Sì.
lei fa questa stessa analisi, un attimino, quando lei fa questa stessa analisi, e non ci mette l'aerodinamica,
Sì.
solamente struttura, cosa ottiene come autovettore di S4M più K W uguale a 0? Otterrà degli S quadro che li verranno tutti quanti J omega, e quindi al quadrato le daranno un meno omega quadro n. E otterrà dei W reali, o no? Se lei qui fa aerodinamica uguale a 0, mette la pressione dinamica a 0, ci avrà S quadro M più K W N uguale a 0. È un problema che lei sa, c'ha soluzioni tipo meno omega quadrato naturale di vibrazione M più K
Mhm.
Z N uguale a 0. E quindi ottiene questi che sono sempre reali, ortogonali rispetto alle medie di
Sì, sì,
bla 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 bla, e questi che sono sempre reali con un meno davanti.
giusto, sì.
Ok, e quindi c'ha le vibrazioni non smorzate e i modi propri di vibrazione della struttura.
Sì, sì,
E gli autovettori Z gli vengono reali. Nel momento in cui gli vengono complessi, e quindi complica le cose perché ci mette dentro quelle E di S con N, ci mette quella matrice aerodinamica, aggiunge le forze aerodinamiche a bilancio del suo sistema interne, forze aerodinamiche che si autoeccitano, ovviamente avendole messe dipendenti dalle variabili modali. In quel momento lei ottiene che questi autovettori sono complessi. Autovettore complesso vuol dire però sempre a coppie complesse coniugate, così come anche i poli, sempre complessi, cioè gli vengono numeri complessi ma a coppie complesse coniugate. Infatti prima gli veniva J più o meno J omega n, però gli veniva sia più che meno omega n. Lì addirittura venivano immaginari puri a coppie complesse coniugate. Qui gli vengono, possono essere anche con parte reale, ma sempre comunque costituendo una coppia complessa coniugata. Anche gli autovettori le vengono una coppia complessa coniugata. Quindi se lei prende il modo elementare che le viene rappresentato da una coppia, perché lei si ricordi che qui abbiamo utilizzato una coppia noi, nel caso reale non è importante utilizzare la coppia, ma nel caso complesso sì, perché noi abbiamo fatto, vede, questo è più complesso coniugato.
mhm,
Io ho preso il critico, ma di critico ce n'è uno sopra e uno sotto pure,
certo.
Quindi lei prenda l'esponente con il coniugato e l'autovettore complesso critico più il critico complesso coniugato, li somma, gli viene una quantità reale che è questa. L'abbiamo direttamente considerato noi la coppia qua. E questa coppia dà luogo ad una vibrazione del tipo che abbiamo appena visto, che è nient'altro che una vibrazione con una stessa frequenza, ma nello spazio in grado di sfasare gli oscillatori, cioè in grado di sfasare le oscillazioni dei diversi punti del corpo, mentre la vibrazione reale mette tutti in fase i punti del corpo durante la vibrazione. Chiara la differenza?
Sì, 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 beh, poi tanto ci devo ritornare sopra, però sì, era per focalizzare bene il punto.
Il modale strutturale è di un corpo elastico, sono onde stazionarie, e questo è il punto, sono onde stazionarie. E quindi durante il moto vibratorio ogni punto materiale vibra con la stessa frequenza di ogni altro punto, ma in fase con ogni altro punto. Qui no, ogni punto vibra sfasato rispetto ad un altro, con la stessa frequenza ma sfasato. E questo sfasamento le dà luogo ad un effetto visivo di un'onda che si muove.
Sì, l'effetto quello che ha fatto vedere con la penna in mano.
Esatto, quello che ho fatto vedere, spero si sia visto anche con... Ma è quello che vedete in quell'aereo in volo, o
Sì,
no?
sì, 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 si vedeva bene.
Avete capito? Beh, se avete capito questo, avete trovato, diciamo, avete penetrato dei concetti fisici importanti di questo corso. Mm?
Mhm. Sì, sì, grazie.
Che cos'è una vibrazione che nasce da un'interazione tra un fluido e una struttura? Com'è fatta la vibrazione che nasce dall'interazione tra un fluido e una struttura? È fatta così.
Questa è la profonda differenza tra le due.
È una vibrazione in cui la struttura si prende energia dal fluido, dalla corrente fluida. E siccome la corrente fluida è imposta, di energia la può prendere quante ne vuole, perché c'è il propulsore che spinge e che manda avanti, ok? E per poter assorbire energia, questa trasmissione di energia non avviene attraverso un moto ondoso stazionario, come può essere quello modale, che è un modo ondoso, quello modale conservativo, sono onde stazionarie. Stazionarie, che vuol dire stazionarie? Stazionarie. Mentre c'è un modo ondoso di questo tipo, sempre ad una sola frequenza. Tu vedi una frequenza, però nello spazio vedi una trasmissione con quella frequenza. E come fai a vedere una trasmissione? Basta sfasare un punto su un altro. Come fa a camminare la lumaca? Hai mai visto come cammina una lumaca mettendola su un vetro?
No.
Eh, eh, vai, vai.
Un po' di lombrichi, prof.
Bravo. E questo svela come si fa, come si può, ci si può muovere in un mezzo con un moto oscillatorio. E i pesci come fanno? I serpenti d'acqua come fanno a muoversi? Vedete più di una frequenza, ne vedete una di frequenza, no? O no?
Sì, sì.
Sì. No, alla fine uno se ne rende conto, però. Ok. Ok. If you have any other question, I'm here.
E prof, stavo dando un'occhiata all'esercitazione 2 e diciamo la velocità di flutter e la velocità di divergenza le possiamo estrapolare solo per via grafica, per come è impostato il codice, no? Cioè,
Fino a un certo punto, poi potete zoomare come volete. Allora, innanzitutto, la velocità di divergenza potete trovarla anche analiticamente.
sì.
Perché la velocità di divergenza dovete cercare un polo nell'origine, quindi mettete k uguale a 0
Annullo tutti i termini in S.
e trovate la O infinito tale che k sia 0, quindi fate il determinante vi viene un'equazione da 4 soldi che vi dà analiticamente la U di divergenza, perché cercate un polo nell'origine, quindi mettete la condizione di avere un polo nell'origine, mettete k uguale 0, sapete la funzione di Odorzene quanto deve valere per k uguale 0? Deve valere 1. Ok? Togliete tutta quanta la parte con le derivate, prime e seconde, perché no? Cioè dove c'è k mettete 0, quindi alla fine vi trovate una matrice 2x2, il cui determinante deve essere 0, in corrispondenza del... Quindi fate determinante 0 e trovate l'unica incognita che vi rimane è un infinito a cappello, che è un infinito di divergenza.
Sì, sì. Va
Ok?
bene, va bene. Sì, 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 va bene.
Il discorso della divergenza può essere generalizzato anche nel caso generale, perché nel caso generale voi potete in condizioni di divergenza trovare la U infinito o la pressione dinamica direttamente, questo è interessante, in corrispondenza di S o di K uguale a 0. Allora, per S uguale a 0 sparisce la parte con la matrice di massa, rimane la matrice di rigidezza e rimane l'aerodinamica valutata per K uguale a 0, che è una matrice 2x2, che è il valore della GAF, della matrice aerodinamica, per K uguale a 0. È una matrice reale, e quindi voi avete rigidi K meno pressione dinamica per la matrice E uguale a 0.
Sì. Sì,
Quando è che si verifica questa condizione? Quando il determinante è 0.
È 0.
E lì avete le stesse equazioni del carico critico, nel quale invece di avere una matrice di rigidezza e una matrice differenziale, avete la matrice di rigidezza e la matrice aerodinamica. Quando è che l'aerodinamica cancella la rigidezza strutturale? Perché alla fine avete due matrici di rigidezza, che sarebbero la matrice di rigidezza e la matrice aerodinamica per k uguale a 0, che diventa una matrice di rigidezza.
Sì, sì, che è parametrizzata per la pressione dinamica.
È parametrizzata solo dalla pressione dinamica, esatto. E quindi vi trovate il valore della pressione dinamica per cui quello è 0. Diventa un altro problema dato valori, se vuoi, però che non vi servono tutti gli autovalori, vi serve il primo positivo, come nel caso del buckling. Vi serve il valore più basso della pressione dinamica in cui quella cosa si verifica. E di fatto quello che sta facendo l'aerodinamica è togliere rigidezza alla struttura fino a che rende la rigidezza nulla.
Sì, infatti poi si parla di rigidezza generalizzata in quel caso, no?
Sì.
Sì, abbiamo fatto una cosa simile alla triennale, però considerando solo il modello aerodinamico stazionario. Comunque sì, va bene, grazie.
Ma con chi?
Con il prof Gasbarri.
Ah, ok. Sì, sì. È chiaro che siccome l'aerodinamica non stazionaria, per K che tende a 0, tende a quella stazionaria,
Sì.
Metterci l'aerodinamica stazionaria, cioè CL per alfa, 2π greco per alfa, va bene, ma solo per trovare la divergenza.
Sì.
L'ho spiegato?
Sì, sì.
E allora, domanda banale, quando voi vi calcolate la velocità di flutter di divergenza con il modello di aerodinamica completo e poi con il modello di aerodinamica stazionario, ottenete per la velocità di flutter due velocità di flutter diverse. Una giusta, quella che vi dà il modello non stazionario, e una sbagliata, quella che vi dà quella che vi dà il modello stazionario, ma sbagliata, eh?
Sì.
Perché altrimenti non avremmo fatto un corso di velocità se non fosse così sbagliata.
Sì, sì.
La divergenza invece, la velocità di divergenza, dovrebbe essere la stessa.
Sì, beh certo, anche perché ho il polo a 0.
Perché in condizioni di divergenza le forze di inerzia non ci stanno, le forze di rigidezza sono quelle, e l'aerodinamica, nel caso di divergenza, è un'aerodinamica, si riduce all'essere la sola aerodinamica stazionaria.
Sì, sì, ci sono. Va bene, grazie prof.
Prego. Okay. Now I would like to introduce to you another exercise, exercise number 3, which is essentially the same exercise of exercise number 2, but performed by a commercial code. In particular, I want to propose the following. I want to propose this exercise here, which is exactly the same exercise we considered in the exercise number 2, but this is the exercise number 3. Flutter analysis of a typical section elastically constrained with a moving mass. This is a novelty. In particular, this point is this point here. You have this moving mass, vertically moving, elastically constrained to an airfoil. And this vertical moving mass has the role of a fuselage. So this element is an element of novelty with respect to the previous exercise. At the limit, if this moving mass is higher and higher, heavier and heavier with respect to the mass of the airfoil, you will have the same limit case of our previous exercise number 2. Okay, so here we have the possibility to consider analytically, considering also the presence of the fuselage. But we don't have this capability in the previous exercise number 2. Okay, so we have a flutter analysis of a typical section elastically constrained with a moving mass by a commercial code. Commercial finite element code. And this finite element code is able to solve this equation, to solve m s squared plus k minus dynamic pressure es w equal to 0. So is able to evaluate the poles and the complex eigenvector for any U infinite and density, and Mach number if you want to perform a compressible flow. Okay, and this code has a double phase, is able to perform a double level solution, structural analysis, model analysis, and lifting surface thin wing body analysis. So this imply, as you know, no wake discretization. Okay, and so this is the finite element vision. Let me do another simplification. In this case, note, in this case, we use the finite element code in a simplified use, in simplified employment, in the sense that we shall consider concentrated mass and stiffness element. In fact, we have a concentrated element here in the center of gravity for representing the inertia of the airfoil, and we have a physically connected, we are physically connecting this point with this other point with a linear and torsional spring like this and this. Okay, so at the end we will obtain mass and stiffness metrics, but these mass and stiffness metrics are not corresponding to a finite element discretization, but to a originally discretized system in space, like a rigid body concentrated in a point, having a mass and inertia with respect to that point, so translating and rotating. Okay. We can use the finite element code also with this reduction. And now I want to spend the rest of my time for describing this simple finite element representation for a system like this. Okay, and this is a representation of the system in the Nastran. We use Nastran in this case, and I recommend to download, if you didn't do this, to download your Nastran code for a student version for representing this exercise and the next one, which is the last one. Look, this is a very simplified vision of our problem. We have our stream on the left-hand side here. We have a frame of reference given by this x-axis. The x-axis is the flow direction axis in MSc Nastran flutter analysis. So we have this direction and we have this direction for the x-axis. So this is, and here you have a leading gauge line like this, and you have a trailing edge line like this. You have a very, very thin airfoil like this. The chord of your airfoil is 2B equal to C, the chord, and this is equal to 2 meter. So C is equal to 1 meter. Okay. We image in this direction, which is the Y direction. Oh my God. In this direction, we have 1 meter. In that, we are simulating a two-dimensional problem. Okay, so the span, this is the span direction, is unitary. This is the span direction, wingspan direction. Okay, so we have the center of mass here, and we have our Y axis on the center of gravity. And if you see, and we have the elastic center here, the elastic center means that I imagine to connect my spring in the spine with respect to the ground or with respect to the other body. Okay. We have look to this board line here from 101 and 102, and this 101, 102, and this 100 are finite element node locations in the initial configuration. So we have only 3 finite element nodes for describing this concentrated parameter model. So we have here a node, here another node, and here superimposed to 102 also the node 100, and that's all. If you want to understand the meaning of this, you can understand this here. Note, we have that the node 100 and 101 are, look to my, can you see me? Yes, you probably you can. This is my pan, and the airfoil is this other green pan. So we have something like this, and this stick is the stick connecting 100 and 101, just like here. 100 and 101, and this 102 is really the point of the fuselage. In the undeformed configuration, 102 and 100 are superimposed. So we have, look to my, this is 102 is the fuselage, and this is the wing moving with respect to the fuselage. In the wing, we have 2 nodes, this and this, and we have a reason for having 2 nodes, which is an important reason, 2 nodes. And one of these 2 nodes are superimposed to the fuselage node in the undeformed configuration. So 100 and 102, the fuselage, are superimposed in the undeformed configuration. Then the stick 100 and 1 and 100, representing the wing, moves up and down, and this is the fuselage. Okay, this is the situation for representing a 3D model as a 2D model. We are using a nuclear power center for feeding a toy. Okay. Now we want to do this analysis with the identical parameter we used in the exercise number 2. In the exercise number 2, we consider the following parameter. In exercise number 2, we have A equal to 3 mass ratio. We had omega equal to 0.8, a frequency ratio between omega h by omega alpha. We had a undimensional duration moment equal to 0.25, and we have this undimensional distance between the elastic center and 1/4 of chord, or the aerodynamic center, equal to 0.1. And finally, this is CE, CE, and CG, which is the distance between the center of mass and the aerodynamic center, like equal to 0.3. So these are the data of our cases, and here we have considered a dimensional case for finite element model, setting B equal 1 meter, and so C equal to 2 meter. As you can see here, you have just discussed this point, but we also fixed the reference omega alpha frequency in radian per second, like equal to 100 radian per second. Okay, and we also fixed the air density as equal to 1.22 kilogram per meter to the power 3 as air density. So by fixing this value, we transform our undimensional set of parameters into a dimensional one. By using this, we have this dimensional set. For example, of course, when you have an undimensional like this, you are representing a class of problem with the same parameter. But by using Nastran, or by using any kind of commercial code in dimensional way, we have to choose one representative of this, one representative of this class, and the representative we are considering is exactly the representative having this 1, 2, 3 parameter established. Okay, all the other dimensional parameters are then evaluated. For example, we can evaluate the mass per unit length of my structure. In fact, we have the undimensional A equal to 3, and remember that A is the ratio between the structural mass and the fluid mass, like the cylinder. Remember, the cylinder of air material, and so the mass of the air cylinder is exactly equal to rho air density by pi b square by 1, and this is the cylinder volume. And this mass corresponding to the value 3 assumed by 1.22 pi b1 to the power 2, we have 11. We have the 1 by, we have 3. Yes, we have pi. And so we have 11.49 kilogram per meter, because we have a meter of wingspan length as a reference for the mass. So this is the mass of the structure corresponding to this mass ratio and this dimensional parameter. We can also evaluate J alpha, for example, which is the moment of inertia with respect to elastic center. So equal to moment of inertia with respect to elastic center, but per unit length. Again, per unit length. And this is equal to the mass, the physical mass evaluated, by the gyration radius, dimensional gyration radius, but the dimensional gyration radius is the undimensional one multiplied by b, okay? And then take the square of this quantity. And this is the moment of inertia with respect to the elastic center. And in this case, we have 2.78 kilogram meter square per meter, okay? Because we have all quantity per meter. Okay, then we have again the principal moment of inertia with respect to the center of mass, and this is, as using the usual rule, this is equal to the moment of inertia with respect to the elastic center minus the contribution of mass by distance between center xg and xe, okay, to the power 2. If you do this, okay, let me show you the geometric offset of our problem. In our problem, in the original exercise number 2, we have C equal 0.1. 0.1 for xe means that the distance between the elastic center and the origin of this axis, which is on the 1/4 chord, is 0.1. 0.1 b, but b is 1 meter, so 0.1 meter, okay? So this means that the distance between 1/4 chord, which is something like that, this is 1/4 chord, which is 1/2 b. The distance between this and this and this is 0.1. In fact, look, we have the distance between here, the leading edge, and the center of mass is 0.8. The distance between the center, the elastic center, and the center of gravity is 0.2, and therefore from here to here you have 0.1. Okay. Okay. Because here you have, this is from here to here is 0.5. Okay. So you have 0.1 and 0.20, which is this 0.3, which is the difference, the distance between 1/4 and the center of gravity. In fact, we have that the distance between 1/4 and the center of gravity is 0.3. 0.5, 0.3 is 0.8. Okay, so we have a physical distribution of our characteristic point, which is compliant with the undimensional quantity used in the exercise number 2. Okay, so the distance between center of gravity and the elastic center is 0.2. This distance is 0.2. And then you can use the previous quantity for evaluating your principal moment of inertia with respect to the elastic center, which is 2.78 kilogram by square meter per meter. Okay. Oh, excuse me. This is not. This is 2. Excuse me. Excuse me. This is the moment of inertia with respect to the elastic center. Here we have 2.41. 2.414. And so this value is lower with respect to the 2.78, of course, as one can expect. Okay. Okay. The last two quantity to be evaluated are the spring stiffness KH, which is the stiffness of this spring KH, and also we have the spring of this rotational spring, which is K alpha. This quantity are quantity KXF are Newton per meter by meter, because we have all the parameter per unit length. Therefore, here we have KH is equal to mass per unit length by omega square h. And we have omega square h because we have omega alpha, and so omega h is equal to capital omega by omega alpha. Capital omega is 0.8, and so omega h is 80 radian per second per meter. And so here we can develop this, so obtaining mass is equal to 11.49 by 0.8 to the power 2 by 10 to the power 4, which is omega alpha square, and we have 73,588 radian per second per meter. Excuse me, not radian per second, Newton per meter. The last parameter to be evaluated is K alpha, which is J alpha by omega square alpha, and we have all the quantity, and so this is equal to 28,745. So at the end, we have a set of all dimensional parameters like the mass, like the moment of inertia with respect to the elastic center, the principal moment of inertia, the stiffness, the rotational stiffness, the linear stiffness, the omega h. Okay, and so we have completely evaluated all the physical parameters for our analysis. Next, we have to consider our practical model to be implemented in Nastran. Okay, so for Nastran evaluation, we have to define the grid, location, we have to define the stiffness, stiffness of spring, mass, and moment of inertia. Location of the lifting surface, in the sense that we have a center of mass, we have an elastic center of mass, center of gravity or center of mass. We have a COG. We have an elastic center. But we may have an airfoil like this or an airfoil like this, having the same COG and EC location. So we have to define the position of the lifting surface, leading gauge, trailing gauge, the opposite. We have to define the lifting surface position with respect to the structural position of the other characteristic point. And so we have leading gauge, trailing gauge, and trailing gauge. So we have to decide this position. And at the end, we have to define the flutter parameter setup. So in particular, define the evaluation of aerodynamic metrics, GAF metrics, and define flight parameter for locus. Okay, so this is the setup for flutter analysis. And we have just to consider and fill a text file in particular. We have to consider this text file. This is a text file of about 327 lines. Most of these lines are comment, and as most of you are know very well, the comment character in data input Nastran file is the dollar symbol, like that. Okay, so whenever you see dollar, you have comment in your data input file. Okay. Okay. go. Okay. Okay. So I would like to skip all the introductory comment on about the structure of a Nastran input file, but I know that most people, present people, are very confident and familiar with this kind of data input. But I have just to introduce the fundamental concept on this data structure. In particular, the Nastran input file we are going to use. We have a data input text file for any kind of model, an aircraft or a typical section. You have always a test file. This is important. And this data input file is, as a name, like a DBF file, bulk data file. The extension is, the standard extension for an Nastran file is this, and this is a text file. This file is an input for our solver, and we will use as a solver the solver solve for solver 145. 145 is the Nastran solver for flutter analysis. As output of this solver, we will have a test file with standard extension as any kind of a output file for Nastran with the extension of type .f06. So if you have a name, if you have a file name here, you have file name .bdf as file input, or which is the same .dat as for data, and you should have as output file name .f06. Okay, so let me practice with you, and I have here the data input file. The data input file is 2D Theodorsen.dat. I have this data input 2D Theodorsen.dat, and this is my input file that I will show you as a structure, as a data input, blah blah blah. And now I can launch my Nastran code here with this icon N. I have a navigator for reaching the data input file, and now here I am in this directory with my navigator by this window, and I click on 2D Theodorsen.dat file, open, and here I have this icon for running my Nastran, and clicking on run, I am currently performing the aeroelastic analysis, and I have my solution here, and this is my solution in the file F06. Look, I have the same file name. No, excuse me, there is some problem. I don't understand what happened. Okay. I'm sorry. I have seen another directory. Excuse me. I consider a different file. I saw another directory, not the correct one. This is the correct directory on my desktop. So this, I want to erase this file and then Nasran icon, click, open, and launch. Look here, I have a generation file, and then the Flutter analysis is completed. Okay, if you see the F06 output file, you have this output, and just to be roughly in the description, you see here, for example, look, you have the real model analysis, and these three are the first frequency, the second natural frequency, and the third natural frequency of my system. The first natural frequency is practically 0 because I have 10 to the power minus 10, so I have a rigid body motion because my system is not clamped to something, because my system is a free system. My system is a free system. In fact, look here. You have this body with this constraint, which is a slide constraint here, and you have this body connected elastically with this other body. So the overall system is a free system, free to move vertically. So you have a rigid body motion. For this reason, your first eigenvalues is 0 in the model analysis. The model analysis is the necessary preliminary analysis for any kind of Flutter analysis, because we want to represent our problem in modal coordinate. So we have originally some mass and stiffness matrix, not diagonal. We want to rewrite your problem in modal coordinate, because we know that the Flutter analysis has to be performed in modal coordinate for the sake of economy of your problem, because you want to study your problem in a limited bandwidth with a minimum number of degrees of freedom, as you know. So this is the preliminary model analysis, and you have also the eigenvector corresponding. This is the real, remember, real eigenvector. Yes, this is a real eigenvector because this is a structural analysis, not yet the elastic one at this level. So we have three nodes, the node 100, the famous node 100, the famous node 101 and 102 representing the fuselage and blah, blah, blah. And here you have the displacement in terms of translation rotation of such a node. So this is the real eigenvector analysis. And at the end, you have also the aeroelastic analysis. You have the complex eigenvector. Together with the value of the pole. We don't have the value of the pole here. Okay, because I have a flag in my. However, this analysis is a PK analysis. Look, the British PK Flutter middle. This is just a view for you for see what we have to understand in order to go in deep in our analysis. Okay, so what I want to do is a fast description of our data input, the file .dat, and the data output, the file .f06 that I have just shown to you. Okay, and so tomorrow we will describe in detail our data input, in particular our file 2d_torsion.dat. And as you know, this data file is divided in three parts. In the first part of the data file, you just have to declare the kind of solution you are interested on. So we are interested to solution of solver 145 Flutter analysis. In the second part, which is this here, this is the second part of our data input, you have just to define the method you have to use for model analysis and for Flutter analysis. This method is clarified by a label. So your method for structural analysis is labeled with 13, and your method for flutter analysis is labeled with number 3. Okay, and so corresponding to this 13, you have here later, let me find 13 now. Thank you. Excuse me. Method 13. Agar L. So this is the card indicating that you are using the numerical eigenvalues approach for determining your structural frequency, which is the Lanczos method. And so you have Agar L for Lanczos, and this is the label you have declared before. However, we will see this structure tomorrow in detail, and tomorrow I will describe to you this data input, and I will describe to you the data output, which is the input-output quantity for performing a flutter analysis. We will have a flutter analysis for a section airfoil, but the interesting thing is the following. You will have the identical data input file also for an actual aircraft. Okay, and this is the message. This is the same kind of input file for an aircraft. And that's all. I will see you tomorrow in the afternoon for another lecture, and thank you very much for your attention.
Prof? Sì, scusi, mi sono perso un attimo perché abbiamo definito due nodi che poi effettivamente sono coincidenti.
Perché indicano una coincidenza geometrica tra la posizione ideale della fusoliera e dell'ala. Allora, la penna è la sezione. Allora, questa è la direzione, la penna è in direzione dello span.
Sì,
e
ok.
quindi sulla sezione tipica, che è questo mio blocchettino qua,
Sì.
io ho messo due nodi in direzione span e la sezione tipica fa così. Va bene, mi vede?
E ecco, la metto meglio. Sì, ci sono.
Ok, quindi lei c'è una sezione tipica che è questa,
Sì.
con due nodi che sono gli estremi della penna. Ok,
Esatto.
e poi c'è un terzo nodo. Ok, c'è un terzo nodo che è il nodo della fusoliera. Ora la fusoliera e l'ala, nella condizione deformata, sono due punti, coincidono inizialmente. Siccome lei quando dai grid sta dando le posizioni della configurazione deformata, lei sa che due nodi coincidono, cioè sa che il nodo 102, che è di fusoliera, e il nodo 100, che è di ala, insieme con il 101, che è ancora di ala, il 100 e il 102 coincidono, ma di fatto il 100 e il 101 sono di ala e sono lo stick che le ho fatto vedere, che distingue, ok? E rappresentano l'ala che trasla. E il 102 è il punto di fusoliera che può coincidere con il 100 di ala.
Sì.
D'accordo?
Sì.
Nella configurazione deformata. D'accordo?
Sì, ho capito. Grazie.
Prego.
Arrivederci, prof.
Arrivederci.
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 Professore, scusi.
Sì.
Posso farle una domanda sull'esercitazione numero 2?
Sì.
Nell'ultimo punto in cui dice di applicare il modello aeroelastico all'aereo completo, io ho fatto...
Dovete fare un'operazione tipi di quella che abbiamo fatto noi oggi, cioè dovete partire però al contrario,
Sì,
dovete
diciamo,
trovare i parametri dimensionali